All right. Hey, folks. Oops, let me just click that randomly. So, forgive me, I am just getting everything set up and started here. Let me do quick clear my environment here. All right. Do a sanity check before we get started. Good. So, welcome to Study Hall. Hope you're having a good, y'all are having a good day. Let me open up the Study Hall Slack thread. If you're viewing this, go ahead and post something in the Slack thread. Say hi. Feel free to say hi. Just post something just to let me know you're here, and that'll help me get a sense of who's around. The primary purpose of Study Hall is to give you all a venue to ask any questions, and I'll give answers and explanations. If you're struggling with something in Learn, you can feel free to send in a link to the problem in Learn, and just a description of your issue. And if the description is just like, hey, I'm having trouble with this, can you help me out? I'll do my best to help you out. So let's see if I can adjust this a little bit. That's better. Hey there. So yeah, so since I'm not seeing any questions at the moment, and do feel free to put them in at any time. I might not take them, if I'm in the middle of something else, I might try to wrap that up or get to a stopping point before I jump into your question, but I will get to it as soon as possible. So since I'm not seeing any questions at the moment, we have a couple options. I haven't really thought about too much what I want to do today, but we can either go through the Learn material, or we can go through Code Wars problems. I've done Code Wars problems the past few times, so I think it'd be cool to go through, or I think it'd be just a nice change of pace to to just go through the Learn material, and we're kind of near the beginning here, so I might just kind of try to just kind of chug through this stuff, and maybe we'll get into something a little more interesting later on. But yeah, if anybody has any requests, if you want me to go through Code Wars problems, or you have a Code Wars challenge that you want me to do, provided that it's doable within the time that we have in front of us. If you send me like a 4, I'm gonna be like, no, not for Study Hall. But yeah, if you have a problem or any requests, feel free to put them in there, and I will ignore them as I see fit. I mean, anyways. Okay. Why don't I shut up and get into something coding related? All right, so looks like we left off on the common data types portion before. So this is just going over floating point numbers and integers and Booleans. Let's see what all this is going to cover. Describe the basic properties of Python's 3 most common built-in types. I'm not sure that I would say that these are the most common, but they are pretty common. We do use them a lot. Maybe they are the most common. And this is going to cover the use of the type function as well. So the 3 data types that this is going to talk about are int, float, and bool. So these are actually our numeric types. These are all 3 considered the Python's numeric types. So let's just look at those real quick. We know an integer is just a whole number. It could be positive, it could be negative, it could be 0. And Python integers can be like any size. They can be huge. If we wanted them to be that, let's do divided by 2. I don't know. We'll just get half of this number. See if that works. There it is. Okay. Yeah, so Python integers, pretty straightforward. They're just numbers, as we would think of numbers. When numbers have fractional components, we express them with a point value. We call those floating point numbers. We don't call them decimal numbers. You're probably used to calling them decimal numbers because that's generally what they're called. But in programming, we want to, we think about numbers sometimes in other bases. A lot of times we think about numbers in base 2 or a base 2 adjacent base, such as base 16 is really common. Hexadecimal is base 16. You'll hear about hexadecimal. And that's just a base 16 counting system. Sometimes we'll use other bases because we're nerds and maybe we want to count in base 6 because we feel like it for whatever reason. So we don't call them decimal numbers because decimal means, you know, the root is dec, meaning 10 DEC implies 10. So we want to use a term that refers to numbers with a point value, a fractional point value that doesn't communicate a base 10 system, right? So we call them floating point numbers to just mean that it has a fractional value. Now, of course, Python numbers are expressed in base 10. They're expressed, you don't have to worry about learning other bases just to do basic math. You know, if I'm expressing numbers, that these numbers are going to be understood as base 10 numbers. Yeah, so floating point numbers, same deal. They can be positive, they can be negative, they can have equivalent values. So 4.0 is the equivalent value to 4. These are the same in value, but not the same in type. We can have a floating point 0 value. So we can do whatever we want. There is a limit to the precision, and I think there's a limit to like the size in general of the accuracy that a floating point number can be expressed. So there is essentially a functional limit on the size of a floating point number. So if I do this, we're going to see 0.9, and then let's add, I think we're up to 15. Okay, let's add another one. Here we go. Okay, so, you know, in this case, I'll run this. In this case, I'm printing off 1. And you might look at this and you might say, oh, well, that's cool. You know, Python just looked at this number and it's like, well, hey, you know, let's not get crazy. Let's just round that to 1. You might think that this is an intentional feature. It's not actually. You might say it's convenient. It might be useful that it's rounding a number that's getting extremely precise. But this is actually, your computer tries to process this value and it can't. This is just a bunch of numbers, 0.999, a bunch of 9s in a text file, and it tries to reconcile that with a number, a floating point number that your CPU can comprehend and comprehend, and it can't. It is physically limited in producing a number that is that precise. So computers are what we refer to as finite precision systems or finite precision machines, and as such, my computer literally thinks that this is the number 1. It doesn't. It's not doing me a favor. It just can't tell the difference, right? So this is a limitation of the machine. Now, the limitation's pretty far out there. The odds of me really needing more precision than this are pretty low. There are ways around this limitation. I think what you got to do is like find a library that has a floating point type that is capable of handling more precise numbers, but we're not going to get into that. We're just going to accept this limitation because, it's got to end somewhere, right? Cool. So that's just a quirk of floating point numbers. This is actually called a precision error or a underflow, an underflow error. And that's when the number becomes so precise that the computer can no longer accurately represent it. And I just mention it because it's not a problem. It's not something that you run into that often. Might be something that you run into occasionally, but it's like if you don't know that there's a precision limit to a floating point number and you're expecting that there's not, it's not common that you will need that, but if you do run into that scenario and you don't know that that can happen, it can be really confusing until you do a couple days. I had a friend who that happened to, and it took them like a couple days of research to figure, and then they learned, oh, computers are finite precision machines, and this isn't going to work. So, anyways, I just mentioned that. Just file it back there. Okay, and we also have Boolean values. So Booleans are technically considered a numeric type. They're technically considered a numeric type in Python, but their values are just true and false, right? So they don't really work like numbers in the way that we're used to numbers to working. In the way that we're used to numbers working. So just true and false. Now these are sort of in Python. These are not just syntactic sugar for integers. In other languages, they actually are. And like C, that true and false values exist, but there's just like a wrapper, a shell around 1 and 0. But we can sort of, interestingly, sometimes we can treat these like numbers. If I do, well, first of all, let's just print them off. We'll just print those off, true and false, no big surprises there. We can actually treat these like numbers, so let's just multiply each of these by 8, right? So if you look here, true times 8 is 8, false times 8 is 0. So true functions as if it's the numeric value 1, and false functions as if it's the numeric value 0. So that's just something that's worth remembering. Or it's something, well, it's almost not worth remembering. It's something that exists. Let's put it that way. It's something that exists as a feature in Python. So Boolean values are useful for, determining. We use them in control flow. So when we get into like if, elif, else, those will check conditions. Those conditions, a condition, when I talk about something being a condition, I'm referring to any part of the code that will express a Boolean value. In other words, any part of the code, any expression that yields a true or false value, any expression that gives back a true or false value. Okay, cool. So I did a couple of these. We just got the last one. What will the following code output? Oh, I forgot about the type. I forgot to mention the type function. Type. There's a function called type. T-Y-P-E. I'm going to assume everybody knows print. Print just, whatever we give to the input of print, whatever we pass into the parentheses there, is just going to be made visible in the terminal, right? So type just takes in an object and just returns its type. So if I want to know the type of true, we'll get a Boolean. If we want to know the type of 8, we'll get an integer. If I want to know the type of 0.0, we'll get a float. And we can use this, we can use the type function for any type that's built into Python, or I think any class in general. It'll just give you the class name essentially. It's a very useful function. Obviously, it might not seem useful when I'm just passing in something that's where it's obvious, right? Like, you know, if I want to know the type of 5.3, like, well, I just typed in 5.3. It's no big mystery, but you know, let's say I have a variable x, and let's say I have a and b. So let's say a equals 10 and b equals 37, and x equals a times b to the power of a squared times the square root of b, right? So this might not be quite as obvious what type this is going to be. I've got these two integers. You might say, oh, well, x is going to be an integer, but I'm doing some mathematical operations, and notice I have a single slash division here. Single slash division always yields a float, even if either or both of its inputs are integers or floats. It doesn't matter. The output is always a float. It always results as a float. So since we're introducing that float into this expression, it's probably going to return a float. So if I want to know what the type of x is for sure, this will tell me. Numerical result is out of range. Okay, so I've probably made a number that is unfathomably, oh, this is an overflow error. So I've made this gigantic number that I can't represent. So let's maybe do some smaller values here. Let's just do 3. How about that? So that's a float. Okay, that's interesting. That's fun that I got that. Let's just print x. I want to see what the value of x is. Well, yeah, that's a pretty big number. I've got a lot of exponentiation going on there, so it's not surprising. So that's going to give me a float. It's going to give me a big floating point number. Cool. By the way, just for some context with type, as you code, inevitably, you know, you'll write some code and you'll run it and it won't do what you thought it was going to do. Your two best sort of debugging tools, your frontline tools that are going to, you know, you're going to use all the time are going to be print and type. And notice that, you know, I'm using print to see what values there are. And when I'm using type, I'm actually putting the type inside a print so I can see it. We need to do that as well. There's other uses for type as well, but we'll kind of get into that later. Okay. What will the following code output? So this double equals will check for equality between the left and right hand side. So 6 minus 3.0. Anytime we do an operation between a float and an integer, a floating point number can represent an integer value. 3.0 is a value that could be represented as an integer. But if I subtract 3.0 from 6, I'm gonna get 3.0, you know, I'm gonna get it's gonna evaluate to a float. And that's sort of just a safety mechanism. Since I can represent any integer value as a float, but I can't represent any floating point value as an integer, for the sake of consistency, anytime we do a mathematical operation that involves a float, the expression will return a float. It'll evaluate as a floating point number. So that's important to know. So the type of a float equals to 3, right? So 6 minus 3.0, integer 6 minus 3.0 as a float is going to give us 3.0 as a float equal to 3 as an integer, and that is actually true. Print 3.0 equals 3, you're going to see that that expression is true. So this checks for equality and tells me true or false whether the left and right hand operands are equal, true or false. So these are equal in terms of their value. They're not equal in terms of their type. So I'm trying to get the value of this expression, and you can see here this expression gives me true. What's the type of true? So if I did type of true there, I'd get a Boolean. Check answer. We're good to go. Cool. I got a little activity here. Let me catch up on questions. Just wondering, for study halls, are we primarily going over the last session's homework assignments, or can we go over anything challenges? I don't deliberately go over homework assignments for premium prep stuff. There's a lot of folks, this is related to premium prep, but it's not limited to only premium prep folks. I think there's a lot of folks in here that come to the study halls that are in basic prep and stuff. And it's not that we're not doing homework because we want to like shield it or anything. I mean, the homework's just going, just sections of the material. But yeah, I don't try to follow the homework per se. I just try to kind of take my time and go through the material, give people an opportunity to stop me and ask questions if they have questions, or say like, hey, I'm working on this. If you're working further ahead in the material, which probably most of you are, because we're like right at the beginning here. I think this is the first section, so if you're working ahead from where I'm working through here, feel free to just pop in a question if you're stuck on something and say, look, if you want my help, and I'll be happy to help out. Yeah, so I'll just kind of go over, whatever's in front of me, or I might do Code Wars problems. Sometimes I'll schedule something specific. Not so much recently though. And then another one, here to absorb knowledge as well. Can you get into specifics regarding floating point numbers and the concept of underflow? Seem to have some confusion with this concept. Thank you. Specifics, the concept of underflow. Okay, so I deliberately don't want to get too specific because I don't want it to be, it's actually not something that you need to understand to know, like for example, to get through the TI, you don't need to understand how overflow happens. You need to understand that it can happen. That's not even going to come up on the TI. It may well, you could spend years of coding and it may well never come up. It depends on the kind of problems that you're solving. It's interesting the way that it works. If you think about how you would store and process information on a CPU and in RAM on a computer, right? So there's objectively more things that you have to keep track of with a floating point number. And we can reduce this down to just working in binary or any base. It doesn't matter what base. On the hardware level, we're working in a binary context we're really working. It's not even binary. Binary is an analogy for what's happening on the hardware level, which is high and low energy states in doped silicon medium, right? Silicon crystal medium. So you have high and low energy states, and we call high energy states a 1, which is an analogy, and low energy states a 0. Sometimes we'll call that on and off. Off isn't really totally off, and on is like a range of current flow, and off is a lower range of current flow. So yeah, getting into all of that, how does it has to do with the computer's ability to keep track of where the dot goes, while also keeping track of what the actual value is, in a way that, as a binary number, can be extrapolated to a base n number, probably base 10, right? So given that you have to not only keep track of the numeric value, but keep track of where that dot goes in that value, right? And that's the analogy to floating, is that dot can move in that number, right? So can move. It could be at any location, so it floats. That point floats. That's how we think about it. So given that amount of information, it becomes more and more difficult as you increase the size of the number to retain that amount of information. So I think, let me look at this. We might be able to make a pretty neat observation about this. I believe it's going to be 15 digits of precision. So that's going to be 1. That's going to be, okay, so it fails right here. You know, this is still accurate. This is inaccurate. So let's just mark these. Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 digits of precision. 16 is an interesting number in binary because it's a power of 2. So it's 2 to the, what, 2, 4, 8, 16. Is it 2 to the 4th? Yeah, it's 2 to the 4th. Am I like, oh gosh, I have to actually do this. 2 to the 4th. 16, yes, it's 2 to the 4th. So what this tells me is that there are 4 bits. There are 4 bits that are designated for counting where this decimal place, excuse me, where the floating point goes in this number. That's my guess, right? So if you want more of a like what's happening under the hood, however this number is stored in memory, my guess is the first or last 4, I forget exactly how that's ordered. I think there are different orderings of it, but my guess is that the first 4 bits of storing that number involve where that decimal place goes, and then the rest of the bits are devoted to expressing the actual value. Hopefully that helps. I'm trying not to get too into the weeds there, because like I said, and you know, anybody listening to this, like, this is an interesting topic, and it's something that like I like this stuff. I read a lot about it a while ago, and to be honest, I'm a little rusty on it, but I can't can't get into all the details on it. I like this stuff. I think it's neat, but it's not. It's also not important in the in terms of like, okay, you're trying to learn what you need to know to like get proficient in Python and like get to the point where you can pass the TI and learn the language and become proficient and competent in problem solving with Python. It's definitely something that's useful to know, like maybe like in like really advanced coding, but in a more beginner of this particularly is a little off topic, but I don't mind the occasional. I mean, to those of you who are familiar with my streams, and I like a good digression, a good tangent. I always appreciate a good tangent, but I do want to make it clear, right? Like this is not. Don't focus too heavily on that. Okay, I think I've made that clear. But good question nonetheless. It's always good to kind of explore and just kind of learn random stuff. Let me know if that was a helpful answer, or if you have any other things. Okay. Can I explain the best way to gauge our readiness for the TI? I know there is a prep for TI module, but other than that, is there another way to do the self-placement challenge and complete it within the suggested time frame? Okay. This is a good question. It's one that I get all the time, and it's a very difficult one to answer. It's hard to like give an answer because I don't know, like without like knowing like where a given person is at, it's just hard to say. It's hard to generalize an answer that's going to work for everybody, or even for for a few people. I hate to just put it that way, but like this is the central question at the the philosophical heart of my job. How do we determine if somebody's ready? For the DSI, and then how do we determine if somebody's ready for the TI? If I work with somebody, one-on-one for a while, I'll get a pretty strong sense, and I'll say, oh yeah, you could probably give the TI a shot. You could be ready. Or maybe hold off, maybe in a couple weeks. So if I know where somebody's at, I can kind of have a sense of that with some accuracy. In terms of general rules, what I notice, so the things that I notice, having done this for a couple years, and not only being an educator, but also somebody that likes to learn programming languages. Like I like to pick up different languages that I hear about just cause, and it's not that I'm a master of all those languages. It's, I like to dabble and play around, and some I dive into, and some I just kind of play around with for a minute. And so I think about learning from the perspective of a learner and also from the perspective of an educator. So having a couple years experience under my belt, things that I notice that help me and that help other people. Of course, everybody's different. There will be variation in this. A lot of it, depends on prior experience. If you have experience in a mathematical, technical, engineering related field, that usually helps. That usually helps a lot. It can help in certain, I think, disciplines of humanities studies and other things as well. But that aside, the things that I've noticed that do seem to have produce consistent results are, well, consistency. Practicing every day, and it's like what I have to say is probably the things you expect me to say. It's probably not like, groundbreaking, earth-shattering paradigm shift advice. It's really just kind of straightforward. The things that I notice that get people ready are, if somebody practices consistently, it's better to, I'd say it's better to do maybe 6 hours of practice interspersed throughout the week, a little every day, 20 minutes here, an hour there, 30 minutes, hour and a half, once or twice a day. It's also fine, if you have a few, like, okay, I'm going to study for 4 hours or whatever, a few big study sessions. It's better to do that than to like cram for 8 hours once a week, 8 or 10 hours, on a Sunday or something, right? I tend to notice people that like do a little every day progress quicker. The cramming approach, I know that's what's available for some people. If you have a family and a life and a job and all the things, you're like, I'm busy in the week and I've got time on Saturday or Sunday and that's it. That'll get you there, but it'll be slower and kind of harder in some ways. So I really can't speak highly enough for consistency. In terms of like actually gauging readiness, as sort of a loose metric, we kind of talk about like getting through 80-ish or more % of the learn materials. And I treat that as a loose metric because it depends on, like you can get through one of the challenges and it, like if you work at it a really long time or whatever, or you just kind of like push your way through it and kind of forget the concept really quickly, that's one thing, but if you get through about 80-90% of our materials in learn, and you feel basically comfortable with it, and that's a metric, that's something that's subjective that like you have to kind of decide for yourself. But if you look through that material, the things that you've done, and you're like, do I at least basically get what's going on here? You don't have to have perfect recall. You don't have to have like perfect understanding of everything in there, but like looking at the problems and saying like, okay, yeah, I see why I need a for loop here, or I see why I need a while loop instead of a for loop, or I see that I'm writing this function that's calling this other function that I wrote, and I see why that's useful. Those kinds of things. If you get through the material and you have that sense of looking at what you've done and what you've accomplished, you have that sense of like, this makes sense to me, more than this is just confusing and I just did this and forgot about it. That's a really good sign. You're probably ready at that point, right? I say getting there is sort of the thing. I think it ends up being, in a lot of cases, just time on task. It's kind of what it boils down to. How much time are you spending on this? How consistently are you spending time on it? If you're spending time inconsistently on it, you're kind of working against forgetting some of the information. If you're doing a little bit consistently, you're sort of dredging up information that you used yesterday. even if it's not the same information you've used recently. So you're sort of reminding yourself, okay, I learned this, now let me remind myself of how that works. I learned that a few days ago, let me remind myself this is how it works. And you're kind of reaffirming the knowledge sort of constantly, and that counts for a lot. And then as much time as you can spend on it solving kind of arbitrary problems. So that's I think that's where like Code Wars and other like coding practice sites comes in into play and can be really useful. Just getting time on task. So yeah. Anyways, I hope that's helpful. I know that's a little vague. I hope someday to be able to say, well, I've got the answer for you, but as it stands right now, that is a difficult question to answer. So, looks like there's a follow-up. No problem. Are there mock TI sessions? I know for the SW Bootcamp, they have mock sessions prior to the TI. We do have a mock interview floating around. I was using it for a while. I did a couple like mock TI sessions. I honestly didn't find that they were very helpful. What I found more helpful, I mean, and I will send you our mock interview if you want that. I'll post it in the study hall, channel, so everybody can access it. Might give you some idea of kind of what the questions are going to be like. The interviews are different enough that I don't know. It's hard to say, but what I found, like when I've aside from just like showing you the mock interview that we have, what I've found more helpful in terms of administering a mock interview is just doing mentor sessions with people. If I'm going to take my time to like watch somebody code without saying anything, it's a better use of my time and your time that be treated as an actual interview. If we're doing that for the sake of seeing, okay, if we did this for realsies, would you have passed? It's probably a better use of our time to say, let's work on a problem and work through it together. You tell me what you don't understand, and we'll work through it together and kind of explore the paradigms and the ideas and the problem solving patterns and strategies in an active way to actually like help you progress towards that point. And if we do that, which anybody here is welcome to just send me a DM and say like, can we arrange one-on-one mentoring? That's most of what I do. I'm available for that. Tovio is available for that. We have several other members of the team who you may have interacted with who do one-on-one interviews, one-on-one mentoring. That's a big part of what we do, what we offer. So if we do that and we're working on something together, like that's actually giving me a really strong sense of whether you're ready or not. And if I'm working with somebody, I will tell you if I think you're ready. We're working on something and you're good to go. I'll say I think you should do the TI. So that can be a way to get some help for that. But yeah, I'll try to track down that mock interview and post it in here so people can download it and at least look at it. I won't make any promises about it giving you 100% accurate idea of what the actual interview is going to be like, because they're all a little different. They're all fairly different. So hope that helps. Cool. Yeah. If you're interested, just send me a DM. You're going to send me a DM now to the person asking and anybody else who wants one-on-ones. Feel free to just send me a DM now, and I'll get to it and either today before class or tomorrow morning, and we'll work something out for later this week or next week or something. Cool. We got another. Could I wax philosophic? Oh, could I? Could I wax philosophic on how to use mentorship? I've done almost all the learning in my life solo. Yeah. Well, the mentorship, my mentor sessions with people will tend to look pretty different depending on who I'm working with. They'll kind of tend to evolve into something pretty different. Some people like to work on, like to bring me code wars problems. Some people like to work through learn problems together. Some people like to bring me problems from books or whatever. I have some people who are like, I want to explore this like really esoteric machine learning concept. And, there's two branches of that. One is that they know Python and they're good at it and they want to like learn data science to make sure that they're ready for the DSI. And I'm like, well, I'm not here to teach you data science. I'm here to get you ready to learn data science in the DSI, So in that case, I'm like, you should take the TI. You're ready. Don't worry. You know, this is a topic that you're actually going to learn in the DSI, right? And the other branch of that is somebody who wants to explore a really esoteric machine learning concept or computer science concept, and doesn't know programming yet. And I have to say, okay, well, that's great. That's exciting. I like that too. We need to like focus on basics and just learn, get you up and running with basics and um, learn problem solving patterns and good workflow habits and basic parts of the language and things like that. So it can look kind of however you need it to look, however you want it, wherever you're comfortable working. I just always try to find somebody's sort of like growing edge, like where problems that are challenging but doable. Um, yeah, that's sort of the guiding principle. Is just find something that like makes you have to scratch your head, but that you can still do. And if you can't do it, you can always, I'm always happy to just walk you through it and walk you through a solution. Um, I think there can be a lot of value in that, and just like, I don't know how to do this, so I need to like see somebody else do it and see a solution. And it's actually kind of funny, um, because you can see a solution and then like try to reproduce it, and there's a lot of value. There can be a lot of value in that. So, but yeah, I'll send in a a Zoom link and a REPL link, so we'll have a shared editor that we can both work out of, and we'll meet in there and just work on problems together. So I don't know if that's really like about like how to use mentorship, but that's kind of how I see it. Like it's really tailored to like what you want to work on and where you're at. And yeah, pretty flexible. So just so long as it's, I'll try to keep us constrained within the scope of what's relevant for excuse me, for preparing for the actual DSI. So hope that helps. Cool. Good questions. I appreciate the activity, the conversation. We get some good stuff going on in here. Yeah, and if anybody else has any questions, feel free to pop them in. I'm not seeing any at the moment, so. All right. Let's just move on. We'll get into the next section here. This is kind of a blunt change of topics. We're talking about like TI readiness and stuff. No, let's talk about basic arithmetic operators. Sure, you don't need me to teach you like basic math and stuff, but yeah. Basic arithmetic operators. I'll just go over these really quick. This is just going to talk about how to do arithmetic in Python. I'm going to gloss over this. I won't go over like an exhaustive example of every kind of combination of ways we could do everything here. But for the examples that I'm going to give, just take note that I can use integers and floats kind of interchangeably. Obviously, the operations themselves will dictate what the result is based on the values, based on their operands, their inputs. Some of those operations will yield floats sometimes, some will yield floats all the time, some will yield integers. So like the return types are a little complicated. So what the expressions evaluate to, it's worth noting, whether it's an int or a float or whatever, what kind of value we're getting back. But for the inputs, whatever input I show, know that we could kind of do an int or a float or whatever. They're interchangeable in mathematical operations in Python. Okay, so okay. All right, let's talk about doing a math. So let's just print. We can just do addition with the plus operator. Big surprise there. Subtraction. Multiplication. Division. Now here's where things get weird. Division. So we got three sort of division. Oops, did that one wrong. Division related operators here. We've got single slash division, which is going to be kind of probably what you expect if you do division on a calculator. It's going to be what it's going to do. So this kind of division is always going to give a float back no matter what its inputs are. So we'll say always evaluates to a float. So what this is going to do, even if I don't even think I need to like give examples of these. These are straightforward. Multiplication uses the star operator, but oops, let's do this. Division is worth giving a few examples of. Oops, dang it, because it can be a little tricky. So if I do, let's say I do 10 over 2. We know that 10 over 2 is 5. 10 over 2 is 5. 10 and 2 in this case are integers. 5.0 is the result. And the reason it's going to give me a floating point number is that, think through this a little bit. Think about this. Imagine you're designing the language. You're designing a programming language. You have a decision to make. What's the best decision to make? What's the best way to treat a division operation? Do you want it to, if I do 10 over 3, well, that has to be expressed as a float, right? It absolutely needs to be expressed as a float. With this kind of division, right? There's another way we can approach division that says like, well, how many times does 3 go into 10 without going over? How many whole 3s can I fit into 10? And that's this kind of division. Double slash division, which is called floor division. We'll get to that in a second. But presuming that we're not doing floor division, let's do this. Presuming that we're not doing floor division, we're doing, more accurate non-floor division. Some operations will need to be expressed as floats, right? 10 over 3 has to be expressed as a float. 10 over 2 doesn't need to be expressed as a float. It could be expressed as an integer. But is that actually a wise decision? Why might that be desirable or undesirable? In my opinion, Python makes the right decision, and I think I don't know a programming language that doesn't kind of have this same ethos. If you have an operation, you should be able to count on the type being the same, always giving you back the same type for a given set of inputs. So you want the type that it evaluates to be kind of easily predictable. And in this case, it would be weird that sometimes if you give two integers, you divide an int over an int, sometimes you get an int and sometimes you get a float. That'd be like hard to predict, kind of. There'd be times when you'd be expecting an integer and you'd get a float, or expecting a float and you get an integer, and it'd be weird. So for the sake of always returning the same type for the given type signature of the inputs, in this case, int over int, will always yield float. So int over int should always give me the same thing, whatever that is, right? Now, if I change the types, it maybe, you might say, well, it could give me, if I change the input types, it's okay to change the output type to match that in a given operation. But so for the sake of consistency, since sometimes one integer over another integer has to be expressed as a float, any integer over any other integer should always yield a float, so that it's consistent and so that you know how this is going to operate, right? So that's why that is. Some people will think, okay, so floor division always gives you an integer, right? That's not quite the case. So if I look at this, let's do 15. 23 over 5. Okay, so first of all, if I do 23 over 5 single slash division, right, 4.6. 5 goes into 23 exactly 4.6 times. 5 goes into 23 4 times without going into a float, right? So it might look like, okay, so floor division always gives you an integer. A lot of times you can count on this. Sometimes you can't. So if I do, for example, if I do 5.0, well, it's the same value, but look at this, right? So since one of its operands, one of its inputs is a float, it's going to assume a float as the evaluation type. So it's going to evaluate to a float this way. So that's important to know. And it's important to know because say you want to use the result of this as an index into a list or a collection of some kind, which sometimes, or you want to use it to like limit a range. It's important to know this because range has to take in integers. Even if you have a whole number float, it won't work in a range. Let's look at this. Range 5. That's going to be fine. No error. But if I do range 5.0, well, 5.0 is the same value as 5, but I get an error. Type error. Float object cannot be interpreted as an integer. And this is telling me if I look into this, this is going to tell me that even if even if this makes sense in terms of its value, range sees this float and it's like, I'm not even going to try, and it's going to throw that error. And that's actually probably the right behavior, really. If you think about this, you know, what does it mean to have a range in from you know, 3 to 8.7? You know, do I pick the smallest increment that I can fit in that space and just iterate that many times? Do I just assume that I'm going to go up to but not include 8.7, so I'd go to 7.7, and then maybe I could assume to truncate that and turn that into an integer. So I'd go up to 7. You know, like there has to be some layer of expectations of assumptions that range is making, and that those kind of being able to expect those assumptions kind of gets more complicated and more complicated. So for the sake of creating something that's easy to anticipate how it's going to work, you just build in some limitations. You just say, no, it doesn't work like that. I'm going to throw an error, right? You know, if you wanted to catch that error, you could use some error handling on that, but we're not going to get into that. Cool. So it's important to know if you're doing a division operation and you want an integer, you want it to resolve as an integer. What I like to do is to just cast it as an integer, and there are lots of times where you want to do this. Just cast it as an integer. So if you have something that you want to that you're dividing, you want it to resolve as an integer, you can use / division and just cast it as an integer like this. And now it doesn't matter. 23.487 over 5.9. Oops, over 5.9 as an integer. Here we go. Of course, this is going to be the same, right? So even though this is / division and both of its operands are floats, it's always going to give me an integer because I'm saying, hey, well, whatever that gave me, just turn it into an integer. And this is explicit. So I like to do things this way. If I need something to resolve as an integer and I know it needs to be that type, I prefer to do things this way than this way. I think a lot of people are like, oh, well, / feels cleaner. And it might, and there's times where you could probably get away with it and it's just as safe. This to me feels maybe a little less clean, but it feels more explicit. It's like, yes, whatever that resolves to, whatever value it resolves to, its type resolves as an integer. So I can count on it. I have a guarantee, and I have, you know, even if in a given context I may have the same guarantee from a floor division, depending on the context, and you know, if I'm using, if the operands are like parameters from functions or things like that, right? I might have the same guarantee effectively, but it's not explicit, right? That guarantee is clear, right? So that's why I prefer to do things that way. So just remember, if you ever need something, a floor division operation to resolve as an integer or a division operation, just cast it as such, and you have that guarantee, and you have the clarity in your code of what you intend to do, which is nice. Cool. Okay. Finally, we have, so that's division. Things get a little weird with division. Finally, we have modulo. So modulo just tells you the remainder. If you're familiar with, if you remember, if you were taught long division by hand like I was in grade school, you might recall the quotient that you get is the floor division style quotient, right? So you get a quotient that says, you know, A goes into B this many times with a remainder of whatever. So modulo just gives you the remainder after doing floor division. That's all it does. In terms of combining this with ints and with like floats or negative numbers, things get weird when you start doing that. I haven't really been in a situation where I've needed to do that also. So don't worry, like the contexts for using modulo tends to be limited to integers in my experience. So you don't have to worry about all that as much. As long as you're sure that the inputs are standardized to the types that you want them to be standardized to, then it should work within expected limitations. So if I want to say like 10 mod 3, I suppose I should clarify this. I want to be extra clear on this, right? If it's not clear, it looks a little small. I have the text blown up, but the way this character is printing, it's kind of a funny looking character. This is the percent symbol. We're used to thinking about that as a percentage symbol. Has nothing to do with percent in Python. You can think about it as the remainder operator. So what's the remainder of 10 over 3? What's the remainder left over after doing 10 over 3? That's 1, right? And if I do 11, that's going to be 2. And if I do 12, that's going to be 0, right? So a lot of times we use this to see if some number is divisible by some other number. You know, we could do some number over 2, and this will tell us if that number is even or odd, right? So depending on the value of n, 37, that's going to be, oops, n equals 37. That's going to be false, right? Because n mod 2 gives me 1, and I know that because it's an odd number, right? So we'll tend to use it in this context a whole lot. Maybe even like that. Oops. So modulo is useful. We tend to use it only with integers as its input. We get integers out. Okay, cool. Oh, I actually had something to talk about. I didn't even think, I was like, we're talking about basic operations. Okay, so what is the result of the following operation? I see 4 over 2. Well, since we're using a single slash, I know that's going to give me 2.0. What is the result of raising 4 to the power of 1/2? For anybody who doesn't know, this is a quick and easy way to do the square root. So, you know, if one of those square root of n, I can say n to the power of 1 over 2. And if I want the 10th root of n, I can do 1 over 10, you know. So the lower term of this division operation is the index. I think they call it the index. It's the right name for that. And that'll give you the ith root, right? And usually we want to do square root. So this will give me the square root of n. So square root of 4 is 2. Since we're using a single slash, right? So this is going to be 1 over 2 is going to be 0.5. So 4 to the 0.5 to the power of 0.5 is 2.0. Since I'm mixing in a float in there, I have to represent it as a float. Oh, and then what's this say? What is the resulting type? Aha! The resulting type of the operation, not the value. Oh, almost got by that one. So the resulting type is a float. Okay. True or false? What is the result of this expression? 9 plus 5 cubed times 7. Oof. So 5 cubed is 15 times 5 is 50 plus 15 is 65. I'm not going to be able to do this in my head. Oh, wait a second. Let's see. I don't need to do this in my head. Okay, good, because this other side is really similar. The difference is the parentheses. So the question is the order of operations going to make this evaluate in the same order as this? And I think the answer is no, because so we have to do PEMDAS. We'll do PEMDAS on this side. So parentheses, there's no parentheses. PE exponent M. So this resolves, then multiplication, then that resolves, then this resolves. Right? Okay, so 1, 2, 3. And then this is going to go 1, 2, 3. So that is a different order. So this is going to be false. Yay. Okay. Cool. All right. Perform. So where are we at? Extended arithmetic operations. Okay. I suppose I forgot to mention about parentheses. If you're familiar with PEMDAS or order of operations, you probably have a sense of what parentheses do and why. But basically, just to be clear on this, we can use parentheses all over Python, not just in mathematical expressions, but any expression we can use parentheses and the things in the parentheses, in the innermost set of parentheses. So if you have an expression in parentheses that's part of a larger expression in parentheses, the innermost parentheses will evaluate first. So it'll evaluate parentheses inner to outer. And that applies to anywhere where you see parentheses, whether it's in whether they're parentheses surrounding the inputs of a function or a method, or just a set of parentheses just to delimit, some group of code that you want to evaluate first, so you can control the order in which a line of code evaluates. So you say this parentheses evaluates first, then once whatever that produces will be used as a term in the next part of the expression, and if that's in parentheses, that will evaluate and be used as a term in the next part of the expression, right? Inner to outer. Okay. By the end of this lesson, you'll be able to perform and interpret the extended arithmetic operations in Python, cast objects from one type to another, understand the limitations of casting. Common arithmetic operators in programming. Okay. We talked about floor division. We talked about modulo. Casting. So casting it might make more sense if we called it converting. I always thought it'd make more sense if we called it like converting from one type to another. But the term we use is casting. So if I say n equals, or that's t, n equals 10, and we'll just print n, and I say print float, and let's do that. So this doesn't, to be clear, well, let's just run this. So obviously I'm going to see n, and then I get the float version of n, which is 10.0, and then let's go back to n again, like this. Right, so notice passing into the float function doesn't actually change the value of n at all, which it shouldn't. That should never be the case. The functions built into Python obey that constraint. So passing something to a function doesn't change the value of it. But what this does is it says, oh, okay, so I've got 10 as the input, so I'll give back 10.0. So this evaluates to the float 10.0. And then I get n, right? If I wanted to capture that in another variable, maybe I could do m equals float of n, and then I could print m, something like that. Perhaps I do want to change n to be a float version of itself. I can say n equals float n, and that'll change it. So now n is a float. So we can do this from an integer to a float. We can do this from a float to an integer. Let's look at that actually too. So 10.5 as an int. So if I cast a float to an integer, which I was doing when I was giving the example of, I should have talked about casting. I just took it as granted, which I try not to do, but unfortunately I let that one slip by me. When I gave that example about like casting your division to an integer when you want it to be, you don't always want it to be, but when you want it to be an integer, casting it as an integer, the behavior here, you have to think, well, what do you do with the fractional component? Well, you lose information, and what it does is it rounds to the floor. Another way of thinking about that is it just chops off or truncates. We use the word truncates. It just chops that off, right? So whatever fractional component there was to that floating point number, it's just gone. It just removes it. It doesn't round to the closest thing. So if I had this at 5.9 or 10.999, it's going to be 10. So the behavior is very simple and easy to expect. It's just simple truncation of that fractional component. Let's see. We can also cast like anything to a Boolean. This is kind of a funny one, right? So 10.7 as a bool is true. 10 is also true. So any numeric value that's not equal to 0 is true. Any numeric value that's equal to 0 is false. And the reason I'm saying that is we have 0, which is equal to 0, and 0.0, which is also equal to 0. So if the numeric value is not equal to 0, then it's true. If it's equal to 0, then it's false. Just to be clear on this, negative numbers are, when cast to a Boolean, are true. So this is, sometimes we call this truthy and falsy, right? So -1 is truthy, negative any number is truthy, positive any number is truthy, 0 and 0.0 are falsy. So the only falsy values are 0 and 0.0. Okay, cool. So what's the result of this? This is like saying, what's the remainder of 5 over 3? So if I do 5 over 3, 3 goes into 5 once with a remainder of 2. What's the resulting type of the following expression? 5 over 3, so this is floor division, so this 3 goes into 5 once. Since we're looking for the type here, right? So this is floor division. So if floor division has integers, both of its operands are, okay, let me try that again. If we use floor division, where both of the operands are integers, the result is also an integer. That's for floor division, not regular division. What's the result of this expression? Result, okay, so 2 to the 6 mod 3, 6 mod 3, 3 goes into 6 twice. So the remainder is 0 twice evenly. So remainder is 0. So that's 2 to the 0. 2 to the 0 is 1, I believe. Is it 1.0? Okay. What is the result of this expression? Oh my gosh, it's a Boolean. So that's going to be true. I thought this said print. Just in my head, I was like, that's print. Okay. So again, 6 mod 3 is 0. 2 to the 0 is 1. Bool of 1. 1 is truthy. True. Okay. I just totally cheesed that one. Cool. Assignment and incrementation. Oh, all right. I'm thinking, okay, it's a little early. I'm thinking I'm gonna wrap up a little early today since we're getting into a new topic just now. We're getting close to time anyways. We've got about 6 minutes left. So feel free to reach out to me if you have any questions. If you want mentoring, I'm available for one-on-ones. I'm still trying to fill up my schedule. I'm happy to help. It's not, I think a lot of people are like, oh, I don't want to be a bother. I don't want to be a burden. It's like most of what I do. So I'm happy to help anybody who needs it. And yeah, I'll call it here. Thanks to everybody who asked a question, brought in some interaction. I think that's what really makes study hall is kind of come alive and makes them fun for me, and I think for other people too. Let me know if you have any feedback regarding study hall, if there's any audio or video issues, connectivity issues, anything like that, technical issues, or if you have other ideas, suggestions. I may not do them, but also I might, I'm definitely open to feedback and suggestions and things like that if you've got it. Yeah, and if you're in premium prep later this evening, then I'll see you there. And if not, then I'll see you next study hall. Cool. Have a great rest of your evening. Bye-bye.